we keep it very light and discussion oriented so we can all learn.
Yeah.
Hey, Gustavo, good morning. Yeah, it's nicely visible. You can put it on display, I guess.
Right, I can say from the beginning. There we are. Are we good? Can you see my screen? Yeah, very good.
Yeah.
Thank you.
Fantastic. Okay, it's 11:02, the perfect time. So I think the recording is on. Yes. So let us welcome today Professor Subbu Ramakrishnan. Subbu is an old friend. It's a pleasure and a delight to have him. Stochastic dynamics and control, some engineering perspectives. Just a brief bio of Subbu. Subbu did his BTech from Mahatma Gandhi University in Kerala, his MSc from University of Calgary, MSE from Johns Hopkins, and a PhD from Rutgers, all in mechanical engineering. So he belongs to that camp of nonlinear people who get better paid than us, but does very similar things. Following postdoctoral work and a stint as a research assistant professor, he joined the University of Minnesota Duluth as an assistant professor in fall 2014 and was promoted to associate with tenure in fall 2020. He is currently an associate professor in mechanical engineering at the University of Dayton. Subbu's interests are in engineering applications of nonlinear stochastic dynamics and control, and his research has been funded by NSF and the US Army Research Office. He serves as a proposal review panelist for the NSF and also as an associate editor for 2 ASME and IEEE conferences in dynamics and control. Apart from his work, he enjoys Indian classical music, which is nice. He can give us some show today. Is a student of Vedantic philosophy, which is also nice. So am I, and a huge fan of the Woodhouse. Okay, that I used to be. All right, let's get going. Thank you.
Thank you very much, Surjit, for the kind introduction and the invitation to present today. It is indeed a pleasure and a privilege to have this opportunity. Thank you all for joining in as well. So the title of my talk is Stochastic Dynamics and Control, Some Engineering Perspectives. So I think I'd like to begin with a brief introduction by asking the question of why is this interesting and why is this interesting in engineering at this particular time? So clearly, I'm sure we'd all agree that stochastic and nonlinear phenomena are fundamental and ubiquitous, but they are critical in modern engineering dynamics and control in several contexts. So if one thinks of how engineering, a lot of engineering used to happen, nonlinearity, for instance, was recognized as important in problems like, say, aeroelastic flutter and so on. And random phenomena were studied in the context of, say, responsive structures to earthquakes and so on in the 70s and 80s. However, in a vast majority of cases, one was used to thinking about linearization or linearizing about a set point or an operating point of a dynamical system if there were nonlinearities, and then proceeding with PID or some other kind of classical linear control, which of course has worked remarkably well for a broad class of systems, including the Apollo mission and so on. However, we are now in a situation where, as the landscape of engineering has expanded and the interaction with the natural sciences and other branches have expanded, there's a lot of inter, cross, and transdisciplinary work. So then one has to look at stochastic and nonlinear phenomena from a different perspective. And more to the point, they can be exploited to advantage in applications. So for example, if one considers vibrational energy harvesting, in which there's been a lot of interest in the last 15 or 20 years, where the idea is that one harnesses the energy of ambient vibration using some electromechanical system like a piezoelectric element to get an electrical response in order to power, say, small-scale electronic devices and such. So there, it is recognized that if you consider the mechanical degree of freedom, you get a much broader range of frequencies where you can get efficient power extraction if you consider nonlinear mechanical degrees of freedom on the one hand. So nonlinearity enters that problem from the standpoint of efficiency. Now, on the other hand, if you consider ambient excitation, it holds water that it probably needs to be considered as a random excitation. So that's a case in point where you have a modern engineering application where consideration of randomness and nonlinearity become important. There are questions in, for example, soft robotics, where one considers soft manipulators inspired in good measure by the biological world, say an octopus arm, which has remarkable dexterity. And if we're trying to accomplish things in soft robotics, think of the soft manipulators, certainly the range of dynamics imposes nonlinear considerations as well as considerations of uncertain environments and so on. So with that being said, I'd like to proceed, if I may, to talk about three applications today. One is bio-inspired robot swarming, and the second is dynamics of a nano-electromechanical resonator, which would arise in the context of sensing, for example. And the third is very relevant to the times that we live in. That would be consideration of epidemic spread dynamics and control. So without further ado, let me get on to the topic of swarm robotics. So the fundamental motivation here is biological complex systems, say, particularly social insect groups like ant colonies or groups like avian flocks or fish schools. And we observe that they are capable of remarkable self-organization and more generally emergent behavior as autonomous groups without central leadership in uncertain environments. So one big question of interest is whether large groups of robots, swarms, can mimic these behaviors, and potential applications abound where you can think of, say, like search and rescue in hazardous environments and other applications where this would be of interest. So the next key observation is this: natural systems have been recorded to use randomness actively to achieve group objectives. So for instance, ants use random search while foraging for food. Locust swarms use noise to maintain alignment and so on. This has been observed. So when we got into this, this problem or this question, my mentor and I, one experiment that I found particularly interesting was reported out of Australia, where they conducted what is called a Y-bridge experiment on a particular species of ant. So what they did was they had two food sources, and they let the ants forage, and the ants chose the closer food storage. So the way this works is that the first wave of foragers go search a spatial domain, and if they find a food source, they come back, and while they're coming back, they deposit pheromone, which I'm sure many of you would be aware of how this process works. So, and this trail of pheromones serves as a guideline for the next wave of foragers. And depending on the quantity and quality of the food at the destination food sources, the trails get reinforced or otherwise. So that's how this works. So as expected, the trail picked up, as you can see on the figure on the right, it denotes the traffic to those two food sources. So the trail picked up to the nearby food source, and after a while they cut it off. And as you would expect, the trail shifted, the traffic shifted to the other food source. But what they found remarkable, and what they reported as remarkable, was that when they reintroduced the first food source, the colony was able to align itself back. So the way one tries to understand this is, you know, they're always outliers, people who don't follow the group, right? So those guys are always doing their own thing, and while they're doing their own thing, they chance upon something that is of interest as a food source. Then slowly the trail starts building. So there were suggestions that you know, randomness, for example, plays a role in this. So that's one of the things that we wanted to investigate. And around this time, my mentor, Manish Kumar at the University of Cincinnati, and I got into a collaboration with an applied mathematician, Andrea Bertosi's group at the University of California, Los Angeles. And we were fortunate to be supported by the NSF for this work. So we started looking at some of the mathematical models, and then we quickly realized that there was room for improvement with respect to the following points, that you really have to treat the food-seeking and the nest-seeking ants as different species, for instance, simply because of the fact that only the nest-seeking ants are depositing the chemical. And we said, okay, if we want to treat it as a dynamical system, it could be interesting. As a closed dynamical system, it would be interesting to allow a fraction of the ants to change character within some neighborhood of the nest as well as the food sources. And also, one has to take into account the fact that more pheromone is deposited closer to the food source. So there is some kind of nonlinearity, nonlinear deposition going on there as well. So considering all these things, we introduced the following model, and this could be considered as a generalization or an extension of the classical Keller-Siegel model of bacterial chemotaxy, which actually has been applied to ant foraging as well. So if you consider equations 1 and 3, and you throw off the second and the third terms on the right, as well as the third term on the right of equation 3, that would be your Keller-Siegel minimal model, what's called the Keller-Siegel minimal model for ant foraging. So rho naught represents the density of foraging ants, which reacts to the gradient of the pheromone. So the chemical is represented, the chemical density is represented by C. And the random motion, you have the delta operator, the diffusion operating on the foraging ant density. I'll come to these two terms in just a moment. So, and then if you look at equation 3, the pheromone or the chemical diffuses as well, there is some evaporation going on. So what we did was that, like I described in the previous slide, we introduced these two terms, which have got some characteristic functions which allow you to switch on and off the neighborhood around which you want the ants to change character. So fundamentally, the rho naught, the foraging ant density, and rho sub I, so the number of food sources is indexed by I, and then it got the rho sub I, the density of the ants returning from food source I. Capital Phi represents the nest, so that serves as a guide for the ants to come back. And this last term on the right-hand side is a contribution to the chemical from each of those returning ant densities. So we introduced this model, and interestingly, the applied math people also thought that this might be a solution to some of the well-known finite time singularities that the Keller-Siegel model is known to develop. Actually, that work is from Professor V. Nanjundaya in the 70s, who was at the Center for Theoretical Studies at the Indian Institute of Science. So the applied math people also thought that there seems to be another nice byproduct of this model, that this would not have finite time singularities, but we've not pursued that aspect yet.
Subbu, I have a question. Sorry, I missed it. So when you put down the equation, what again is chi and what again is omega?
Oh yeah. So let's say omega sub Fi is some neighborhood of omega sub F sub I is a neighborhood of the food source I. Mm-hmm. So you say within that neighborhood, and chi is a characteristic function that you use to say that if you are within that neighborhood, so let's imagine that an ant goes, collects some food, and then it changes character, right? So I mean, it's coming back to the nest. So a rho naught ant is becoming a rho sub I ant, right?
Yeah. Okay.
So you control the spatial domain or the neighborhood where it happens by these characteristic functions.
So chi is a time-independent constant.
Yeah. It's a constant. It's a characteristic function. Right. Okay. So you can think of it like, I don't know, 0 and 1, something like that. Yeah. Okay, no problem. All right. So then what we did was that we took those equations and simulated them. So we were able to reproduce the experimental results that they were seeing. So on the right, you see the pheromone trails that you see from simulating the model. So initially, you got these two trails, and then you switch off one of those. I hope you can see my cursor. Yeah. Are you able? Yeah. Thank you. Yeah. So, so once you switch off, once you cut off one of those food sources, the trail weakens, and then you reintroduce it, comes back. So And correspondingly, you see the traffic as well. So the one interesting conclusion is that you're able to see the experimental results here. But being engineers, we also want to see how this can work in the real world. So this is Manisha's lab at the University of Cincinnati, where we conducted these experiments. So we took some robots, Kepler robots, mobile robots, and I'm hoping that you can see the action there. So this is certainly a far cry from trail formation, but this was using that model with virtual pheromone to get those robots to cluster. So what you see in the top is actually heat maps or photographs from the top. And here you actually see those robots. So this is kind of proof of concept that you can actually use this Pte model and can be implemented on robots. Of course, we're only too aware that 4 robots do not a swarm make. And sometimes when you submit papers on swarming, it almost feels like you had to prove everything using an Avogadro number of robots. But regardless, we thought it's promising that these experiments were possible. Okay, so with that, we moved on to the next problem of area coverage. So you think about a bunch of robots trying to cover an area, and it could be a very simple or relatively simple situation, like you get a bunch of robots to say, or even a single robot to do carpet cleaning, you're covering area. Or it could be something much more involved as retrieving real-time information, or even searching for potentially mines in a battlefield or something like that. So the analogy, the fundamental analogy, is that you can think of ants randomly searching for food as akin to a bunch of robots randomly searching for information. So that brings in the notion of area coverage. And what's really interesting here is that ant colonies and other biological groups change the type of random search. So, for instance, if they're searching for food and there's a lot of food in the vicinity of a point, then the randomness is could be described by Brownian motion. Whereas once the food becomes scarce in a particular neighborhood, they execute motion, which seems to correlate with non-Brownian processes, such as, for example, alpha stable Levy flights. So, and there's some controversy about this, but some of the work reported on this, for instance, they took extensive data out of the coast of California on marine predators. And the data seems to suggest that these organisms are able to somehow execute, the long flights that they execute if they don't find food in a given neighborhood can be well described by a Levy flight. So the question then was, if you look at the area coverage problem, what can robots learn from this, or how could robots mimic this behavior? So I'll use the word agent for the remaining part of this portion, because these are all in simulation. So one would rather think about a multi-agent system and not an actual robot, because these don't involve actual robots. And for those of you who might not be familiar, allow me to draw the distinction between Brownian motion and a Levy flight. So, for example, in both of these, on the left, you've got Brownian motion, on the right, you've got Levy flight. The starting point is the origin, the same starting point. And these simulations were run for the same amount of time. So you can see that with Brownian motion, you get thus far, whereas with Levy flight, you get much farther away from the starting point. And also, interestingly, it's characterized by these large departures from the mean value, occasional large departures from the mean value, which characterizes Levy flight.
So, excuse me. So only
yeah, sure.
2D problem, have you studied also 1D situation, 1D experiment? I mean, or 1D motivation?
We actually, because we were thinking of area coverage, so it seemed natural to think about 2D. So what we did was 2D. We did not consider 1D.
Okay.
Yeah. So So you have this, and of course the analysis behind Levy flights, as I'm sure several of you would be aware, is a bit more complicated because the diffusion operator becomes a fractional diffusion operator. So that is more involved, but certainly interesting to, if possible, to understand. So and then the way one understands this is also that if Brownian motion is characterized by the Gaussian normal distribution, then a Levy flight would be a fat tail distribution with a non-trivial amount of area under the tail. So then one understands those large departures as being drawn from this non-trivial area under the tail. So what we did for this area coverage problem was that we went back to the so-called Keller-Siegel minimal model. And then, so we wanted to ask the question, what happens if you replace Brownian motion with Levy flight? And more interestingly, what happens if you allow an agent, aka a robot, to switch the search process from Brownian to Levy, depending on the availability of information in its neighborhood at any given point in time? So that's the central question we're asking. So to go from PDE to simulations, there's got to be a way to get a system of ODEs that you can implement in the simulation. But unfortunately, if you think of these equations, the PDEs as probability density equations, or a la Fokker-Planck, then the classical correspondence between the Fokker-Planck equation and the Langevin equation, which I show below that, gives you passage between those two formulations. So essentially, you start with a PDE, you use the Langevin type of formulation to get to those ODEs, with of course that DW being the noisy process, and sigma being the noise intensity. So you would replace that DW with a corresponding increment for the Levy process when you try to do that. So this is kind of the framework, the formulation. And further, we had to go ahead and develop some metrics, performance metrics for the area coverage. So we developed the notion of a percent area coverage integral, which essentially measures exhaustivity. We also developed a notion of visit entropy, which which corresponds to frequency of coverage. And while we were at it, we thought we'll also examine the efficiency of the swarm to detect, say, pop-up threats. So you put in random events within that spatial domain and see how well or how efficient the swarm is to detect those threats. So as a matter of methodology, we defined a threshold fermone concentration parameter. When we say fermone, it's really virtual fermone, or you can also think of it, of course, as information content. So then you define a concentration threshold parameter, and you say that if a robot finds that in the neighborhood, if the threshold parameter is what is the information it finds in the neighborhood is below that threshold, it executes Brownian, and if above, it goes for Levy. So I'd like to show you a couple of plots, and I'd like to refer you to our paper for more details and for more detailed results. But here is the area coverage performance on the left, and there is definitely some advantage that you can see in terms of switching the advantage that you derive by switching between Levy and Brownian and Levy, depending on the circumstance, on the situation. On the right is a very interesting, what I find a very interesting result, because it says that this efficiency happens for a certain interval of noise intensity. So, and in a way, you can physically reason this, because if your movement is too noisy, then you're probably overshooting, or you're not really accomplishing the objective. But on the other hand, if you're less noisy, then you're not getting enough coverage. So this is very interesting, also because it's very reminiscent of things like stochastic resonance, where there's an optimal level of noise intensity, which creates maximal output or maximization. So this we find very interesting and certainly worthy of more investigation. Of course, this is a numerical result. One would like to understand this from the analytical perspective. So to conclude this part of the work, adaptive switching between Brownian and Levy improves search efficiency. Optimal values of evaporation, which can be thought of as information loss, and diffusion coefficient increase the efficiency, and particularly optimal values of noise intensity are critical. Here are some of the publications, and we're happy to share those with you if you're interested. And in particular, we've taken some of this work forward in terms of prioritized foraging strategies. So it's natural to think about what happens if the quantity of food is time dependent, or some depletion in time of food. So if you've got multiple sources, how do you prioritize where you want to go? So we've got some interesting results there as well. And of course, that links to scheduling problems like the traveling salesman problem and so on. So it seems, it appears to be a very rich kind of problem to think about. Now I'm ready to move on to my second topic, or the second application, which would be from an engineering standpoint, I would like to think of it as a sensing application. But it's really the nonlinear dynamics of nanomechanical resonators, which I'm sure many of you would be aware are mesoscopic mechanical resonators coupled to electronic devices. So a point to note is that the remarkable capability to sense physical quantities, they really have revolutionized sensing. And that's closely related to the high resonant frequencies possible with these resonators. And of course, they operate in the mesoscopic regime, which straddles the classical and the quantum regimes of dynamics. Now, from the sensing standpoint, an important parameter of quantity is a quality factor, which one understands as the ratio of the amount of energy stored per oscillation to the amount of energy dissipated. And for a linear resonator, one can show that this quality factor is the ratio of the resonance frequency to the resonance width. So if you look at the frequency response curve, that's how one would define the quality factor. And it's been argued that for a nonlinear resonator with high frequency, you can modify this relationship, but essentially the quality factor is still proportional to that quantity, as you see here at the bottom. Bear with me just a minute as I'm trying to hide my video here. Right. So that ratio characterizes the quality factor, regardless of whether you're looking at the linear or the nonlinear regime. So it's of interest to note that the nonlinearity influences the quality factor. Excuse me. And in particular, there was an experiment reported by Aisha et al., where they experimentally studied a nanoresonator and reported nonlinear damping effects. And they argued that the quality factor can be improved by exploiting the nonlinear damping. So a student and I got interested in this work because that work was followed up in particular also by Roth et al., where they conducted a numerical study and showed that white noise excitation affects the frequency response characteristics, and thereby the hysteresis and the quality factor. When you have, sorry, yeah?
Alex may have a question. Alex, do you have a question? Okay. Go ahead. Alex, you are muted. Or maybe not. Okay, let's move on. Sorry about that. I thought Alex was going to ask a question.
Oh, no problem. Yeah. So Roth et al.
Sorry about that.
No problem. Thank you. So Roth et al. Reported that white noise excitation can influence the quality factor. So there were both of these aspects which motivated us to study what happens, to see whether you can get some sort of analytical understanding of what is going on when you have this kind of nonlinear damping. And this particular damping term of constant eta times x squared times x dot was also suggested in that paper. So that was our basis for considering this. So a student suggested that we should try the harmonic balance method on this. So then we proceeded to get a frequency response relationship, frequency amplitude relationship. It's a straightforward, a little bit tedious, but straightforward algebra where we got that relationship, which you can see on the right-hand side. where X is the amplitude of the response, omega is the frequency, F sub D is the driving amplitude, and those constants are the damping coefficients. Delta is the linear damping coefficient, and eta is the nonlinear damping coefficient. So then we really wanted to compare this with the numerical solution. So we found that there was excellent agreement between the analytical solution based on the harmonic balance method and the direct numerical solution. The one mismatch that we found was actually that subharmonic resonance that you see there, but then that is not surprising at all because by definition, the harmonic balance method assumes that the solution contains only the first harmonics. So therefore one wouldn't expect the harmonic balance method solution to pick that up. So other than that, there was very good agreement. And we further went and wanted to check the harmonic balance method solution against a perturbative method solution. So we did that, and then this was the conclusion that we found interesting, that when you have a relatively smaller driving amplitude, then all those methods seem to agree. But when you increase the driving amplitude, in this case, they go from 0.001 to 0.2, and of course these equations are non-dimensionalized. So you see that the harmonic balance method holds up pretty well against the numerical solution, as opposed to the in contrast to the perturbation method. So that was another result that supplied confidence in the harmonic balance method for this particular problem as well. So then along the lines of Ross et al. And white noise, we wanted to ask what happens when you have Levy noise, what happens to the hysteresis region, and these simulations show that we found that it is much more sensitive. So for example, on the left-hand side, you have between sigma equals 0, which is of course the deterministic case, and sigma equals 0.002. And then on the right-hand side, you've got 0.005. So when you increase the noise intensity, that region that you see that shrinks quite significantly. And it doesn't shrink. You can show that this doesn't shrink as much when you consider white noise. So, so if you have a situation where a nanomechanical resonator is going to be excited by Levy sort of noise, then this effect is definitely significant. And to the best of my knowledge, these nanoresonators under Levy excitations have not been studied extensively. So there seems to be some room, of course, if there is some experimental evidence that this would be of interest. So proceeding, we then try to plot the effect of the noise intensity on the quality factor in the case of Levy. So that's what we see there. So the delta omega decreases as you increase noise intensity, and based on the definition of the quality factor, as the delta omega decreases, the quality factor goes up. So that is the argument to conclude that as you increase the noise intensity, your quality factor actually improves. So these are some of the conclusions, some of which I already mentioned. So in the case of this particular type of nonlinear damping, the harmonic balance method appears to be a very good choice to analyze the motion. And those are the effects on the hysteresis region, and thereby the quality factor. We ran a bunch of sensitivities as well, which have not, I didn't show you the results there, but with sensitivity to the nonlinear damping coefficient, sensitivity to the driving force amplitude, and so on. But this was an important takeaway, or an interesting takeaway, that the Q factor increases with increasing Levy noise intensity. So here are some of the publications. There are a couple of journal manuscripts in the pipeline. Brilliant student, but he's been operating under some version of the uncertainty principle since he graduated. Very hard to localize, but hopefully we are able to submit those soon. So that's the publication on in the pipeline. And finally, I'd like to talk about epidemic modeling, so which I'm sure you would agree is very relevant in the times that we live in with COVID. So one looks at the current models. The vast majority of them are typically ODE based. They're compartmental models where you partition a population into disjoint groups of, say, susceptible, infected, and recovered. And then you have a system of ODEs that goes back to the seminal work of Kermack and McKendrick in 1927, where you study the evolution of these subgroups of the susceptible, infected, and recovered as an infection progresses. And you declare a pandemic an epidemic to have ended when the number of infected reaches either zero or some kind of endemic equilibrium. So you have those analytic models on the one hand, and on the other hand, you've got these purely data-driven types of models. But when you look at it, for instance, if you want to understand the spatio-temporal dynamics of an infection spread, then it appears clear that one needs to move beyond these ODE-based models and start thinking about PDE-based models. Another consideration would be to have improved mechanistic models where you say, okay, all of this happens because of two things. One is human behavior, and the other is really the transmission characteristics or the transmission dynamics of the pathogen that is triggering the epidemic. So in both of these cases, one would want to have some kind of a mechanistic understanding or mechanistic reckoning of those aspects in the model. And the third thing that would be very desirable would be to have some sort of an organic relationship with real-time data, in the sense that one would like to envision a model where you start off with a certain model, but then which the model kind of evolves or can be calibrated in real time based on what you're seeing. Of course, there's a fundamental time delay issue here because there is always a gap between data on the ground and then the modeling. So, excuse me, but to the extent possible, one would like to update the model with real-time data or have the model learn in some sense from real-time data. So considering aspects of nonlinearity, the nonlinearity arises in those ODE models, and there's a lot of work, extensive literature on related to several epidemics like tuberculosis or malaria and all of those things, the flu. There's a huge amount of literature, and the transmission mechanism appears to be captured effectively by nonlinear terms. And I'll point that out in just a moment when I show you the equation. So that's where the nonlinearity enters in a rather natural way. And in terms of randomness, of course, there is human behavior is random. People move around, they diffuse. The compliance with any mandates is also pretty much a random response. Some people would not like to comply as much. So there is randomness in human behavior that needs to be accounted for in this problem. And like I mentioned, so that's something that one hopes that one can control. So, by some kind of mandate, for instance. On the other hand, the randomness that is a contribution from the pathogen transmission characteristics are not controllable. So for instance, if you have some kind of a variant of a virus that transmits, much more significantly, then there's nothing we can do about it. But then, however, you can account for that. You can capture those transmission characteristics with some kind of a random model. So these are the two types of sources of randomness that one would consider in this context. And then finally, one would think of interventions. So interventions can be classified as non-pharmacological or non-pharmaceutical, like masking or social distancing and so on. And then there are, of course, pharmacological interventions like therapeutics and vaccines. And indeed, we know that non-pharmacological interventions are first lines of defense against an epidemic outbreak, because certainly the pharmacological interventions take their certain amount of time to develop. So one thing that is natural to think about is whether you can do some kind of control theoretic analysis that can guide interventions. So these are some of the questions, some of the, to set the stage for what we did. So we started off with the Pte model. This is actually reported by Lee and Zhou in 2009. So this is a compartmental model. So you got S is the susceptible, I is the infected, and R is the recovered. And the L is actually a density that takes care of the latency, and it's just there for accounting purposes. It does not contribute to the dynamics, because if you see the right-hand side of that PDE for L, this term is exactly that term with the sign flipped, and the second term is actually this term with the sign flipped as well. So it's really not contributing to the dynamics of S and I. And if you look at this, you have the diffusion terms in there, so you assume that the susceptible population is diffusing, and you have birth and death rates accounted for. And the phi times I times S, excuse me, sorry, trying to recover my cursor. Yeah, this is that coupling term. So that's really, you can think of that as causing the infection. So the number of infected, the infected density multiplies with S, the susceptible, and some fraction of which is actually getting infected. So this is where what they call the mass action transmission mechanism, that itself is a nonlinear function, but then you can, people have considered more, other types of nonlinearities. For instance, you can have S divided by, or I times S divided by 1 plus some I squared, which would allow for some saturation phenomenon, for instance, in the infection rate, which is what naturally would happen, because certainly if you consider a finite population, then after a certain time, the pathogen runs out of people to infect. So this is a convolution term. So tau is a time delay, which of course you have to account for that latency between a person getting infected and, say, being testing for positive for the infection. But in that time, somewhere in between, they can become infectious, and without having been recognized as being infected or acknowledged as being infected, they could travel a spatial domain and then infect other people or affect the susceptible population. So that's what is captured in this term. So it's a convolution term, and that kernel we've taken to be kind of a Gaussian kernel. So that's what that term does. So all of that, except for that U, is available in the model of Lee and Zhou. So what we did was, try to introduce this U as a control term. So you would think of this U as somehow characterizing, say, social distancing, which is preventing the infection, right? You can also try to introduce another control here in front of the diffusion term. So that would be, one could think of it as, say, stay-at-home order, where you reduce the random motion of people in a neighborhood by control. So we took so the idea was to take this and then take that model and then compare it with actual data, COVID-19 data from both the state of Ohio as well as Hamilton County in Ohio. So that's a map, a grid map, a discretized map of the state of Ohio. And the approach was to discretize the PDE, of course, taking into account the appropriate boundary conditions. So here we have what we call reflective boundary conditions. So you see that so you assume a no flux situation, which I'll talk about in the next slide as well. So you discretize the PDE, and then you think about a learning phase where you try to optimize the model parameters based on actual data or the true data set. And we did that for 30 days, starting April 20th of 2020. And that date was chosen because the first infection in Ohio was reported on March the 20th. So we thought we'll give it a month before we start looking or using data for this analysis. And you're trying to, the optimization is with respect to a cost function that looks like that. So you N sub C is the number of counties, and capital T is the time for which you do this. And in this case, the discretization timescale is very natural because data is updated every day. So that is your timescale. So you try to optimize the model parameters. with respect to that cost function, and then you let the model tell you what it thinks where the infection is going for the next, say, 10 days. And then you question how accurately the model can predict the actual infection spread. So this was kind of the approach that we took. Certainly, the approach comes with a set of assumptions. So the model parameter is assumed constant for the time period of the simulation. Actually, I think that in a more complicated analysis, for instance, if you think about, say, a space-dependent diffusion coefficient, or more generally, state-dependent diffusion coefficient, things could get really interesting, I think, in terms of such an approach. It would get much more complicated, but also might be able to yield more, potentially yield more accurate results. We had no access to the recovery data, so we had to make an assumption. We assumed that 75% of the infected individuals either recover or unfortunately succumb to the infection 10 days after testing positive. There's no flux boundary condition, so you don't allow anybody else to come into that domain during that simulation. So you assume that that's happening. And in terms of granularity, we have to assume that data is uniformly distributed within each county. So we have access only to county data, so therefore we have to make that assumption. So here are some results for the state of Ohio. So just to set the stage, I'd like to focus on the middle one, because that's actually the graph of the infected population density. So the yellow line is the ground truth, or the true data. The blue line is the training phase of the model, so the first 30 days, and then the broken line in orange is showing the actual model output, the model output for the 15 days for which it was tested. So we refused to be disappointed with this, because the trend was, it was showing the correct trend. Of course, one would have liked to see a better agreement between the actual data and the model output. But then, considering the assumptions that went into the model in terms of constancy of parameters and so on, so some error was to be expected, in fact. And it's also true that during those time periods, some counties might have had more mandates than others, so hotspots could have developed. So those are all events that this model cannot account for. So some error is to be expected. And here is a heat map between the actual model output and the true data at the end of the testing phase, which is on day 45. So if you're not aware of the map of Ohio, with that area that you see there, that red hotspot is kind of around Columbus, and the southwest corner there, as you see, is Cincinnati, and on the top right is Cleveland. So those are the three big C cities, the three big cities of, or the bigger cities of Ohio. I certainly don't want to offend anyone in Dayton. So you see that, but then you see that the model output is able to capture somewhat the hotspots that you see around, or the infection spread around Columbus, that area. It does not do as satisfactory a job around the other spots, but still, you can see that broadly there is that trend. And again, for all the reasons that I mentioned earlier, a certain amount of error ought to be expected with this approach. Now, what we did was we introduced what I would call quote unquote controls, kind of open loop. So you know, as an experiment, you just say, okay, what happens if I put in a constant value for the U that I showed you earlier? I wouldn't, there's still some ways from honest to goodness control where you actually take the output and then feed it back into the system. But however, regardless, we tried introducing that control, and then we saw some interesting results. So the blue line that you see is with no control, and the red line is when if you introduce that constant control at every point in the domain or every cell in the domain. And the middle line in yellow is what you see if you do it preferentially. So you say, for a county, if I look at the data for the last 5 days or 7 days, and then start based on a threshold value, I start implementing, triggering that control. So these are some of the results if you do that. And these are some of the corresponding heat maps with control. So you see that, for instance, if you in B is the case 2, which is called case 2, is when you introduce that control uniformly. So you see that the hotspot diffuses quite well. So these are those corresponding results. And this set of results for the county were much more encouraging because you see that the model matches the county data much better than it did these data from the state. So we believe that there could be a lesson to be learned here in the sense that this type of modeling might be more appropriate for a smaller geographical region and for certain amounts of time. But even that information I would submit is quite valuable in the case of a novel epidemic. So here is some comparison of cumulative infections for different control inputs. And one thing that I find interesting here is also that that saturation that you see, which actually you would expect in the case of no control, but here we ran it for a much longer period of time, and you see the difference in the growth of the infection when you try those different types of control inputs. But overall, there's no question that if you can characterize that control and introduce it, you can get a very good handle on how you might be able to mitigate the infection spread. Here are some of publications, and I'd like to just note that Michael Gray there was an undergraduate student of mine at the University of Minnesota Duluth, so it was delightful to have him as part of our team. And Shelley Ehrlich is an epidemiologist at the Cincinnati Children's Hospital as well. So the conclusions and outlook on this, I would submit that Pte models offer a promising pathway in epidemic modeling. The considered model, as I said, seem to yield better results for the county than the state, but of course you need validation with data from other locations for say other time periods. And then of course one has to take into account perturbative events such as super spreading, because it is known, it's been reported, it's well known that events such as super spreading have a disproportionate influence on the progress of an epidemic. So therefore, it's important to be able to characterize them analytically and account for them in computations as well. There are other features such as infection mechanisms with saturation that can be considered. Excuse me. And time delay effects become very important as well. And certainly the notion of techniques from feedback control, say, what would be the effect of stability of the system? One can think in terms of, because of the inherent non-linearities in the model, one would be thinking in terms of, say, bifurcations and other stability problems potentially. And the notion of relaxation. So going back to super spreading, that's the other point I'd like to make, that, for example, if a super spreader event triggers a large spike in an infection, what are the relaxation dynamics to an equilibrium? How does that affect those? And of course, all of this would be most useful if it can somehow guide or serve interventional public health policy. So my understanding is that in several cases they don't have a very good handle on how to implement certain policies, and given the understandable resistance of the public to frequent mandates or extended mandates, I think it would be important for public health policy experts at, say, the county level to have access to, say, a suite of models where you can get some understanding of the range of possibilities or the range of scenarios possible. So that is really the hope of our kind of work, this kind of work, and we hope that we can take this forward and other people take this forward as well. Okay. So it's now my pleasure to acknowledge my collaborators and my students, in particular my collaborator Manish Kumar in mechanical engineering at the University of Cincinnati, has been a mentor, a good friend, and a great collaborator over the years. I'd like to acknowledge him, his friendship and his collaboration with me. Students, certainly these are my students from the University of Minnesota, Duluth. My most recent institution. I just moved this fall to the University of Dayton. So I'd like to thank them, I'd like to acknowledge them for their contributions. And finally, the funding agencies which have kindly supported our work over time. And in terms of students, I'd like to note, if I may, that since I'm just starting and trying, very interested in trying to set up a group at the University of Dayton. So I'd be much obliged, appreciate it very much, if you could point your students who might be interested in this kind of work my way. We have a range of possibilities, starting from summer undergraduate research all the way to postdoctoral opportunities, and we have funding available. So I'd like to request you to send interested students my way. That'd be much appreciated. I've got my email on the first slide here. Launching the funding, and finally, it's indeed a great pleasure to thank you, all of you, for your time and your attention today. Thank you.
Thank you, Subbu. Very nice talk. Fantastic. We are open for questions. So please unmute yourself and ask questions if you have questions. Yeah, Ambika, please go ahead.
Yeah, very nice talk.
Thank you.
It is results are better for county than for the state. Can it be because you have overlooked some heterogeneity that is involved?
Yeah, that was possible, right? So, as I pointed out, we have to assume constancy of the parameters in the model. So that constancy might be a better approximation for the smaller geographical area of the county than the larger area of the state. And it's also the numbers that's involved, right? I mean, the total COVID cases for the state of Ohio, I believe, around 1.5 million. So the numbers that one is looking at, there's so many things that could happen. There could be hotspots that could develop during that time. There could be other things going on. Yeah, so you're right in the sense that the heterogeneity, there's a larger likelihood of all kinds of heterogeneity in the larger geographical location.
Question from Marcel also.
Thank you.
Thank you, Sue, for this nice talk. So I have a comment and question in the first part when you showed that the Levy noise in the hysteresis. So the first part is a comment. So my comment is because you call harmonic balance method. So to my knowledge, maybe this kind of method also is known in the amplitude equation developed by, for instance, Bogolubov in the 60s. So if you see this kind of methods have also developed a long time ago, but I don't know if you know this because I explained that you call harmonic balance. This is a comment. I don't know if you like to comment about that.
I mean, to my understanding and the students' understanding, it was called the harmonic balance method in some of the references that we used. But I'd like to thank you for the comment. I will definitely go and look into it. And in the next talk I give, I might have to update myself.
And you can find easily if you put Bogolubov.
Yeah. No, I'm aware of that. I'm aware of that technique. I'm aware of that name. I didn't relate it directly, but this seemed to be referred to as a harmonic balance method in several textbooks. Yeah.
Okay, thank you. No, and the question is, what happens if in the case of you reduce this bistability region, I mean the coexistent region, when you consider multiplicative Levy noise?
Yeah, that is a great question. I mean, I have a lot of interest in multiplicative noise processes. I'm beginning to get interested in those because I believe there are in several situations that's a better representation of the noise, because it is dependent on the state itself, right? I mean, noise always doesn't have to come from external sources. Right. Unfortunately, I don't have an intuition for what would happen when you have multiplicative noise. But I would agree that it's definitely an interesting question to look at. We're doing some calculations with a physicist and a postdoc in physics and an old friend of mine in cosmology, Monsi John. And there, we're looking at actually, I'm bringing this up only because you asked the question about multiplicative noise, but there, we're looking at things like a stochastic evolution of the Hubble parameter in cosmology. And there, the natural framework is actually a multiplicative noise situation. So the diffusion coefficient, the corresponding Fock-Planck equation actually is dependent on the spatial variable. So the short answer to your question is that I entirely agree with you that that would be an interesting case to look at, but I don't have any intuition of what it might look like. Okay, so I wait for the future when you give me the answer, the definitive answer. Yeah, thank you. Yeah, thank you, Noah. I'll try my best. Yeah. Thank you. Thank
you. Let me ask a question. If Human doesn't have a question, Human usually has a question. So regarding the idea of the compartmental model and so on. So I was quite astounded when I noticed that it took less than about 50 some days for COVID to spread worldwide. And by worldwide, I think the number of countries I'm talking about is of the order of 150. So the CDC has some stuff on it, and there are other sources I can find for you if you're interested. So I was just wondering that instead of looking at the compartmental model at a local scale, which you have, this model may actually be quite good if you actually insert your Levy flight type idea to really mimic people moving around and see if one can characterize the level of movement in some way, given that we know the timeline within which it spread, because pandemics come every 10 years or so, according to data. And COVID aside, it is extremely interesting to see then that if your R value within this context is typically of the above between 1.5 and 2, let's say, in that range. I think COVID is around there, a little over 2 around there. The spread can be so rapid. So, your study with the addition of Levy noise can be ideally suited for looking at the spreading problem. So that's one comment I want to put in.
Yeah, so, I could not agree with you more. Actually, we have an NSF proposal pending at the moment, and one of the ideas in there is exactly what you just said. So it is natural to also think in terms of to wonder whether you can characterize superspreading somehow using these non-Brownian types of processes, right? Because you're getting a huge spike. So where's that coming from, right? So so that's my response to. I could not agree with you more on that one.
Yeah, this should be a relatively straightforward calculation because we know the R values roughly, and one can start an initiation somewhere around southern China, and then just track it and compare with data. That's one thing. Second thing I thought is more of a comment. It's a thought I had. So hanging out with Ryan, I don't know if Ryan is still here. He is. Hanging out with Ryan, I've begun to think in terms of robots more than usual. And, many years ago, in the early 90s, I spent quite a bit of time and energy on this landmine business. Landmines are very complicated because they're 5-6 inches at most underground, and our ability to see at that depth is pretty much nil, because electromagnetic radiation has large absorption, so you are pretty much left with very poor electromagnetic resolution. If you start acoustic, it has to be nonlinear acoustic, because acoustic also has otherwise similar problems. So landmine problem is therefore a very large problem of the order of 110 million mines around, mostly anti-personnel mines. So they're small mines and they're plastic, largely plastic. So robots therefore should be interesting. I'm sure people are trying that. Of course, there's never enough money for finding mines. So it seems to me that if robots can sense mines by looking at the, by essentially sensing the explosive content, right? And that chemists have solved this problem actually years ago. So every robot, a pretty stupid robot, literally, something with wheels or whatever, something that can move with large wheels, can sense in principle where the explosives are. And then the second thing what a robot can do, because the mines have to be taken out, it's not a good idea to explode the mine because it destroys the land. And mostly this is in civilian and agricultural areas. So it is entirely possible that a robot can actually fluidize the bed locally with high frequency jarring, right? And it may actually be possible if it can be locally fluidized, unless it's terribly muddy, to just pick out the landmine by a robot. So the entire problem, because you mentioned this, I kind of mentally went back and I was thinking the problem may be handled quite a bit better. Anyway, I just wanted to say that because I thought this audience may be interested in it.
Yes, thank you. Yeah.
Thank you.
Actually, Ryan is on my list of people to contact because a student of mine recently worked on a nonlinear oscillator network model for a soft robot. So, his Dracula amps that he showed, that's very interesting. So Ryan, if you don't mind, you can, I'll be intruding into your schedule with an email sometime soon.
It's funny that you mentioned the nonlinear oscillator. We, back maybe 5 years ago or something, we experimentally were measuring like frequency and amplitude response of a PDMS single link mechanism that we microfabricated. And we experimentally observed that same like fold over effect for the nonlinear damping. And at the time we were just saying, well, this is just nonlinear damping. And quite honestly, the MEMS community doesn't really care where it comes from. But yes, and then yeah, Surajit and I have been talking about robots a lot lately. I got him very interested. And I personally work on some small robots that could be deployed with the swarming applications, but I work more on the hardware side. So if those are of interest to you too, just let me know and maybe I can ship you some.
Oh yeah, absolutely. Yeah, no, I was not. I was being very serious when I said you're on my list of people to contact.
Very nice.
Yeah. Right. Yeah.
I've been known to mail robots, is what it is.
Any other questions? Please go ahead if you do. Otherwise, we'll close the session. It's about 12:10. Hearing none, let's thank Subbu for a fantastic Saturday morning, afternoon, evening session. And thank you so much for taking the time. And we have a couple of nice talks in October. In 2 weeks, we have Gemanu Gunaratne coming back again to give a second talk. He's the first person to give a second talk in the series. And then Marcel is coming up just around Halloween. So we're looking forward to Marcel's talk as well. And thank you, everybody, and have a great weekend.
Yeah, so thank you again, Surajit, and everybody for the questions and for your time.
Thank you. Bye.
Thank you. Bye-bye.
Bye-bye.
Bye.